Today it's our pleasure to have Anatoly Spitkovsky with us, visiting from Princeton. Anatoly's academic histories, he did his graduate work at University of Berkeley. He was then a JAMRA fellow, and he spent most of his time at Stanford. And then after that, he moved to Princeton, where he's been a professor for the last several years. He's sort of I guess he's known as an expert in high-energy astrophysics and numerical methods applied to high-energy astrophysics. He's worked a lot on pulsar magnetospheres, pulsar winds, physics of collisionist shocks, and I guess type 1 X-ray bursts as well, and probably some other things that I'm not remembering. But anyway, we're happy to have him. Today he's going to talk about why I guess why astrophysicists should know more plasma.
Okay, am I on or should I be? Okay, good. So, great to be back here. The title is a bit strange. So, this phrase, "how process will travel," is sort of a derogatory phrase that my former advisor, John Ahrens, who was visiting here a few weeks ago, is using whenever he sees formal plasma theorists finding an interesting indispersion relation, finding an instability, and then going to town applying this instability to everything in astrophysics and claiming that they can explain everything. So basically, I want to use this phrase as my motto and actually show that in some cases you can actually do that, but not always. So this talk is about adventures in plasma astrophysics. So what's plasma astrophysics? Well, to some degree, everything in astrophysics involves plasma, almost everything. So most astrophysical processes, therefore, should depend on the microphysics of plasma, and we should know plasma physics, right, in order to explain astro. Usually, it's not that trivial. So the difficulty is that the plasma scales are typically much smaller than all the astronomical scales. And therefore, these plasma effects are most often very well hidden. You don't see them immediately. Well, you can just see that by looking at what typical frequencies in the plasma are. Well, they're in the 10 to the 4 hertz for a typical plasma frequency, or the spatial scale is under a kilometer. So all of these are either too fast or too small to be of significant interest to astronomers. However, there are situations when this microscopic physics manages to affect macroscopic physics. And those are the most interesting situations to me to study. Unfortunately, in most cases where this happens, our understanding is quite limited. So what we usually do is we parameterize the unknown microscopic physics, and as a function of some introduced parameters, we are trying to explain the large-scale systems, and as a result, we end up with multiples of models which all explain the data, yet they differ in these fundamental assumptions about the parameterized processes that they use. So by this idea of, we verify our theories by comparing them to data, well, we're stuck, because all of these theories explain the data. But these theories could be eternally inconsistent. So it's nice to be able to actually constrain the theories for a change rather than try to explain the data. So what typical conditions where plasma effects could be important? So I'll just list a few in no particular order. Accretion disks are usually invoked when people talk about unknown plasma physics. Well, the reason for that is that we need some sort of collisionless viscosity to mediate accretion, and there are several advanced candidates for this viscosity, in particular magnetorotational instability, which I'll discuss later, and also the result of accretion in some cases leads to multi-temperature flows. So electrons and ions give their different temperatures. And how all of that happens, how magnetorotational instability works in a collisionless plasma, and how it leads to energy partition between ions and electrons is kind of an unknown problem. And again, it's parameterized. And in order to understand it in detail, we need to know how plasma physics work. Another example is clusters of galaxies. To plasma physics, this is just a big ball of ionized gas. And it also has some magnetic fields in it. And issues of transport end up being important for explanation of large-scale properties of these clusters. So issues of heat conduction and issues of resistivity may affect the appearance of the clusters, and therefore this subject is of quite interest. And this is intrinsically a microscopic thing. You need to understand how what happens in a magnetized plasma and how it transports heat over large distances. Also, cosmic rays could potentially be important as both providing non-thermal pressure and possibly electrons to light up the clusters. Other examples involve supernova remnants. So here again, the issues of electron-ion equilibration come to mind, because naively, if this is a shock of a supernova remnant, if you take the upstream plasma that goes through the shock, the ions and electrons come in with the same velocity. Therefore, you expect them to just thermalize at that energy, and therefore the electrons and ions will have different temperature in the downstream, and the temperature should vary. They should differ by a factor of 1800. In fact, we see evidence of electron heating. So electrons are heated by ions, and they're heated in probably collision-less way. If you look at how long it takes to do it by collisions, it's longer than the sizes that we're actually observing. Also, there is interesting evidence for presence of cosmic rays and magnetic field amplification in supernova remnants. For example, these thin synchrotron rims that you see over here, these blue light, and the thinness of these rims is interpreted as a very fast synchrotron burn-off of freshly accelerated electrons in these shocks. So if you ask how much magnetic field do you need for that, you end up with values that are like 100 times the values of the interstellar medium magnetic field. And that's much more than you can expect in a simple compression of the shock.
What fraction of equipetition?
What
fraction of equipetition field is that?
It's still very sub-equipetition, maybe 2%. One way to explain that has been to invoke cosmic rays and the back reaction of cosmic rays onto the upstream flow that can amplify magnetic field due to plasma instability. So we'll come to that. Other examples of involve what we call non-thermal sources. So these could be both non-relativistic, like supernova remnants, and relativistic sources, like pulsar wind nebulae shown here, gamma ray bursts, and so forth. And here the issues again revolve around particle acceleration, in particular how particles are injected into the acceleration process and where they're accelerated, and that's where the physics of collision with shocks appears again. And also questions of magnetic field generation. In gamma ray bursts, you expect magnetic fields to be created from almost nothing and reach significant values comparable to tens of percent of equipetition. Okay, so another environment where this plasma physics rears its head is neutron-star magnetospheres. And here, almost everything is up for grabs because a lot of the physics of the magnetosphere depends on where the plasma actually comes from and how much plasma is there in the magnetosphere and which regions have plasma and which do not, and so forth. So this relies on knowing how plasma is created, how plasma is accelerated. And recently we've started to appreciate more that these magnetospheres actually carry currents, and the physics of these strong currents actually is important. And we'll come to discuss that later in the talk. Also, the relativistic jets and winds, here the process of collimation and acceleration of the whole jet can be treated well with magnetohydrodynamic models, for example. But then the conversion of the energy into from magnetic to kinetic energy requires some sort of perhaps magnetic dissipation, some sort of non-ideal process, and also the conversion of kinetic energy into emitting particles also requires some sort of perhaps shock acceleration. Okay, so with that in mind, the goals of what I'm trying to do here is to try to model some astrophysical systems using realistic microphysical parameterization. So I'm going to use some microphysics that comes out from the direct plasma simulations. And the trick here is to be able to start on a very small scale of the simulation and to be able to extrapolate to very large astrophysical scales. And this is non-trivial, so I'll show you how I think I'm able to do that. The idea would be then to constrain astrophysical scenarios. So if you have different models, you want to be able to discriminate between them using some sort of realistic plasma physics. Okay, so the three things I'll be talking about are the physics of shocks, and summarize some results, some recent results that we have on particle acceleration and relativistic and non-relativistic shocks. And then I'll talk about relativistic magnetospheres, in particular reconnection magnetospheres. And finally, I'll talk about turbulence and accretion disks. So in terms of the issue of connecting models to processes, how the process will travel idea, what the first subject I'll be talking about is sort of going between the process to the model. So we'll start with a microphysical process that we can simulate inside of a collision with shock, and then try to construct an astronomical application of it. In here, we'll start with modeling astronomical data, and then it will lead us to understanding what kind of processes are involved in this relativistic magnetospheres. And finally, here we'll just discuss what kind of processes could possibly happen in the middle of accretion. Okay, so with that in mind, let's continue. So the tools I'll be using for this is ab initio plasma simulations. This is what's known as particle and cell method. The basic idea is that you disregard plasma as a lot of macroparticles. This is similar to particle mesh idea in cosmological simulation, except these particles carry both positive and negative charge. And the currents of these particles, as recorded on the grid, can be used to advance Maxwell's equations. And then the Maxwell equations provide the electromagnetic field that are used to advance the particles. Okay, so that's one type of code that we're using. This is the most fundamental way of modeling the plasma. It's also the most expensive way of modeling the plasma. We also have what's called a hybrid code, which is a kind of a compromise. So there is ions are still treated kinetically, but electrons are treated as fluid, a massless fluid. And finally, there is a assortment of various MHD and force-free codes that I'm using whenever I need to provide context for the astrophysical setting. Okay, so all right. So let's talk about shocks. So the idea about what's interesting about this collision with shocks is that there is an interesting feedback process that happens that tries to couple the very small scales to very large scales. And this is why this is an interesting plasma physics problem. From a large scale point of view, all you have is just a conversion of a cold upstream flow into a hot downstream flow that's moving slower. And this, in hydrodynamics, is modeled as some sort of a jump, right? So some sort of microscopic physics is involved, but you don't really need to worry about it because this jump just conserves momentum energy and everything else. So in reality, the internal structure of this is collisionless, so you need to provide this viscosity through collisionless means, and this happens due to various instabilities. So there are streaming instabilities and possibly interaction with magnetic fields, which we'll discuss. But the idea is that this happens on tiny scales here. Okay, so this small scale stuff. However, this small scale stuff provides perturbations to the flow that are needed to start injecting particles into an acceleration process. So these small-scale fluctuations is what's starting to accelerate cosmic rays. So the particles are injected starting at this transition, and then the particles can get accelerated as they zoom back and forth around the shock. And then you have a population of cosmic rays which have a non-trivial amount of energy, and then these cosmic rays start to react back on the flow. So now the next step is that these cosmic rays try to stream into the in front of the shock. They amplify magnetic fields. The magnetic field structure through the shock changes. The whole shock becomes more of a diffuse structure because now these cosmic rays are long-range mediators. So this problem becomes a convoluted mess. Okay, but at the same time, you have to always remember about the small scale. You can't ignore the small scale anymore because those small scales is what's injecting your cosmic rays in the first place. If you remove that, then you don't have the handle on how cosmic rays are injected. So, in other words, there is this love triangle between the shock structure, turbulence, and particle acceleration, and they all can affect each other, and they always try to steal the show. So the way we, sorry, I'm having a little bit of coughing issue. So the way we do this in practice, we do a collision between a flow and a wall, and we study the reflection from the wall of a flow which may have initial magnetic field, and then that forms a shock wave that propagates through the medium. And we can vary the angle of this magnetic field, we can vary the strength of this magnetic field, and we can study this in a systematic way. So basically what we're doing is this survey, and since I'm in Princeton, it's called this SDSS, which stands for Systematic Digital Shock Survey. And basically that's what we're doing. We're setting up controlled experiments, and we're trying to do everything in a consistent way. So the main findings of this survey so far is that we've identified how shock mediation mechanisms depend on the strength of the magnetic field. And also we're seeing particle acceleration happen from first principles in relativistic shocks, and recently also in non-relativistic shocks. And we're seeing this process of back reaction of cosmic rays onto the shock structure. So we're seeing the beginnings of this nonlinear feedback. And just as a summary of shock processes which occur here, this is it turns out that the main parameter, the main dimensionless parameter that describes these shocks is what we call magnetization, or the ratio of magnetic energy to the kinetic energy. And this plot shows the magnetization on this axis. So another way to say this is the ratio of the skin depth to the Larmor radius of the particle upstream. And so the magnetization is shown here. It's also an inverse Alfvénic Mach number squared. And different velocities of shocks are shown here. And typical environments where these shocks occur range from these non-relativistic shocks to relativistic shocks over here. And what we found in broad terms is that if the magnetization is small, and typically it's below 10⁻⁻3, so the fraction of energy magnetic field is under 1%. And then the shocks at low magnetization are mediated by this filamentation instability, or Weibel instability. At higher magnetizations, shocks are mediated by reflection. So what I mean by that is that if the magnetic field is strong, then the particle comes in, sees a jump in the magnetic field, and starts gyrating. Okay, so this forward motion, which can be forward motion is slowed down as the particle has to undergo these gyrations on the downstream side. And so that typically these magnetized shocks look fairly sharp. The thickness of the shock is just 1 Larmor radius. If the shock is unmagnetized, this filamentation instability produces these more diffuse and filamentary shocks. So here's a movie of what a typical unmagnetized shock looks like. So here's the density profile. This is the magnetic energy profile through the shock. The flow is incoming like this. This is electron-positron pairs. And you're seeing a jump in the density over here and seeing a magnetic energy that's being created in the shock. So there was no magnetic field to begin with. This filamentation instability happens in front of the shock, creates magnetic field. Magnetic field isotrophizes the particles, and then magnetic field starts to decay. So that's the structure through a typical unmagnetized shock. Okay.
This is 2D, 3D?
This is 2D. In 3D looks pretty much the same.
The magnetic field is similar.
We can't run it as long in 3D, but from what we've tried, it's similar. So our 3D ends probably here. And in 2D, of course, it can run for much longer.
And you see the difference in electron ion temperature.
Right. So this is the pair shock. I'll get to electron ion in a second. So the important features here is you see there are waves in front of the shock, there are filaments of magnetic field in front of the shock, and then there is downstream field, and that downstream field is decaying over time. The interesting thing about these shocks is that you see ab initio particle acceleration. So this is a movie of a particle going through these filaments of magnetic field. This is the upstream part, this is the downstream part. And here we're plotting its energy. And you can see that this particle manages to cross the shock. And every time it crosses the shock, it gains energy on the upstream side here. So now in the downstream, its energy is constant. It's going to cross the shock. And it gets hit by the incoming flow, its energy is increasing. So that's your classic Fermi acceleration at work. And the nice thing about this is that this was a completely unmagnetized simulation to begin with. There was no assumption about the turbulence. All the turbulence is completely self-generated. So any number we get here, in terms of efficiency of acceleration or energy in the accelerated component, is computed without any assumptions. There's nothing going into it. So here's an example of particle acceleration in an electron ion shock with initial magnetic field. So there was initial parallel magnetic field to the flow. And what you're seeing here is actually not energy, it's magnetic field strength. And this is the downstream part, this is the downstream part. What you're seeing is that I initially started with magnetic field that was purely uniform. But by this time, what you're seeing is some sort of waves that are propagating in front of the shock and actually being swept towards the shock. Okay, so these waves have circular polarization, and these are actually non-resonant waves that are driven by the escaping cosmic rays. So this shock can accelerate both electrons and protons, but protons actually travel further ahead of the shock, and the current of these protons drives amplification of magnetic field.
What's defined as the wavelength?
Right. So the wavelength is defined by for non-resonant instability, it's much shorter than the Larmor radius of the cosmic ray. So it's basically like the cosmic ray just going in a straight line. And the wavelength is defined by this amount of current in the cosmic ray. So the more current you put in, the longer the wavelength. And if this is allowed to run to complete nonlinear saturation, then the field will grow so high that the cosmic rays will actually get deflected, and that will trap the cosmic rays. Okay, so the mining shot for pairs, this is the type of acceleration that we're seeing for unmagnetized shock. So this is the downstream distribution of electrons or positrons in a pair shock. So most of the particles have thermalized to their initial gamma factor. So this is gamma 15 shock here. So you see relativistic Maxwellian in the downstream, but you also see a tail. Okay? And this tail is growing with time. So what you see is that this exponential cutoff is moving to higher and higher energy as a function of time, which leaves behind it larger and larger extent of the power line. And
the amplitude relative to the thermal component
right.
as well as constant.
So 1% by number in the tail and 10% by energy in the tail. So that, and the slope is around 2.4 for these runs. And we verify that this is pretty much independent of gamma, as long as the gamma is larger than 5.
Is it independent of time? So is it always 100%?
Well,
This is 2.4.
this is 2.4 is conversion. But, okay, and obviously our times are limited, so I can't exclude a very long-term evolution when, well, actually we do see some sort of long-term evolution. We see the magnetic field start to grow on larger and larger scale in the upstream, which eventually may lead to concave stacking. So there is a back reaction onto the upstream, which will happen on longer time. This is the results for the magnetized shock. So here the different angles represent the angle with respect to the normal to the shock. So along the direction of zero is along the direction of motion. And what you see is, again, there's a downstream Maxwellian. Then 0 degrees shows a nice tail. Interestingly, the tail gets more pronounced as you get to higher inclinations, until some critical inclination beyond which you don't see anything. So 34 degrees and beyond, there is only a nice Maxwellian in the downstream. So what happened here is that this is a relativistic shock, and if you tilt the magnetic field too much, a particle that's trying to outrun the relativistic shock will have to move faster than the speed of light. Nobody can do that, so there is no acceleration beyond a certain angle. So this critical angle is 34 degrees as measured in the downstream frame. In the upstream frame, it's 34 degrees divided by gamma. So basically, we're forcing, if you want to see acceleration in these magnetized shocks, you better have magnetic field pointing almost towards your line of sight.
So that probably isn't true in a lot of the contexts.
We'll come to that. Yeah. I mean, so that's the nice thing about this. If you actually believe the simulations, they can place enormous constraints on your model. And I believe them. Okay, so we'll get to that. So this is the results for electron-ion relativistic shocks. The idea here is kind of similar, but the physics is more convoluted. I invite you to look at this paper by Lorenzo Cironi. So the idea is again the same. So this is the ions. The efficiency increases a little bit as you go from 0 to some critical angle, and the critical angle is pretty much the same idea. It's this transition to superluminal shocks. And for quasi-perpendicular shocks, there is no acceleration. Okay. Electrons also show tails, but their effective amplitude is suppressed with respect to the ions. And so there are still electron tails, but there is, for quasi-perpendicular shocks, we don't see a lot of acceleration. We do see a lot of heating. So the energy exchange between ions and electrons does happen, and it's quite efficient. And we have a few physical arguments for the actual mechanism for this heating. It's a little bit convoluted, it requires positive. So I won't go into that.
Well, what about the ions? What are the modes that are scattering the ions?
Scattering the ions.
Well, I mean, are we thinking about our plane waves here or something different?
You mean to do this? Oh, to accelerate? Yes. So these are these bell waves. So the circular polarized waves that are driven in the upstream are what's accelerating the ion.
What was the mass? What was the mass ratio?
So this one I think went up to 100, and we haven't seen significant differences. It's more than 16, yeah.
And I'm sorry, what's the length back? What's the speed of the shock?
So this was gamma 15, but we tried gamma 50 and 100. And as long as so what we're finding is that relativistic shocks are kind of boring. As long as they're faster than gamma 5, they'll pretty much look the same. Okay, so let's try to put our blinders on and apply this to astrophysics.
So yeah, go back one second. You did say the electrons are heat. They get at the same temperature essentially as the protons.
They get to a good fraction, maybe 30%.
But it's a non-local phenomenon, and you can't describe it by a local
heating? Well, heating happens in the upstream, right? So heating happens as the flow is getting towards the shock. So the particles that are escaping in front of the shock are warming there's kind of a counter stream that happens. And that puts energy into the incoming electron. So that preheats the electron. So when they enter the shock, they're already hot.
And it's basically people can.
Not quite equal.
And that happens 30% shot.
And after that, they're pretty much staying like, there is no extra exchange beyond that.
So, presumably you're going to talk about the non-relativistic.
Yes.
That's the
After
other,
that,
yeah.
yes. Okay, so let's do some applications. So immediately, as Chris mentioned, there are many cases where we know that the field is toroidal. That it's transfers to the direction of the flow. So pulsar wind nebulae, for example, are a good example. What I'm saying here is that if there is a relativistic shock with a toroidal magnetic field, and the magnetic field is appreciable, meaning that magnetization is larger than 10 to the minus 3, then I shouldn't have accelerating particles there. Okay. So what is my solution? Well, my solution is to say that the magnetization is actually smaller than 10 to the minus 3. So you're basically unmagnetized in the shock transition layer. Therefore, you can inject particles and accelerate. The measurements in the graph, for example, are sort of in that limit. So the measurements at the shock, people say that 10 to the minus 3 is roughly the sigma that the magnetization that they infer in order to explain this morphology, this global antisymmetric morphology of the jet and the torus. This has certain implications. It means that the magnetic energy is probably dissipated somewhere in the wind. How that happened, John Ahrens described to you a couple of weeks ago. It's a complicated story. I think, I'm being recorded. It works, John. Yes, it works.
Well, I'm not convinced actually. But the geometry here doesn't obviously correspond to a planar shock. And the shock jump conditions depend on what the relations of the fluid are, way downstream and upstream. Right? And it's possible in this type of geometry that they change with position. In other words, if you slow down the flow a little bit, then you can get reconnection of the magnetic field occurring across the equator, which allows the magnetization to change due to the transverse structure as the flow is accelerating. So it's not clear that there's a simple mapping between the planar shock problem and the crowd pulsar wind structure.
Well, I think the issue here is that the injection happens on plasma scale. Okay? So if there is no global gradient on the scale of hundreds of spin depths, then I think what we're doing is okay. Right? So I mean, the part I'm simulating is the absolutely microscopic part of this picture. Right? So locally, and the injection has to happen locally. It cannot happen on global scale. So that's my argument. That I know what should happen locally if local magnetic field is oriented this way. Okay, so I mean that's one possibility. Another possibility is that the magnetic field may not have dissipated after the shock, but perhaps it's coming in at the shock as a strike. So it doesn't come in all of one polarity, because polarity is alternating. How that accelerates particles, we're not yet sure. So my student Lorenzo Cerny is trying to do these simulations right now. He's coming to very interesting conclusions, which I'm not ready to advertise yet. So that's another possibility, but needs to be explored. So I think PWMs could be understood if the magnetization is sufficiently weak in the equatorial plane. Okay, for AGN jets, situation is a bit more exciting. So here the people infer a lot to have high magnetization toroidal fields. So the jets are supposed to be wound up toroidal magnetic fields. And then the question is, are there shocks in these jets? So we see these bright spots in the jets, but are they really local dissipations due to shocks, or perhaps there is some other process of dissipating energy? If they are shocks, then I cannot make them work. Unless, if they're really relativistic shocks. Because in the proper frame of a jet which is moving in gamma path, the actual shock may be subrelative, not entirely this relativistic. Maybe the gamma factor could be below 2. What happens in that case, we still need to understand. But if they are indeed relativistic shocks, then pure toroidal magnetic field at large magnetizations, I think this has to be ruled out. The alternative is that perhaps it's not shock dissipation, but perhaps it's some sort of second order acceleration. So you have turbulence in the jet accelerating the particle. Another possibility that the magnetic field is probably reoriented. People talk about the sheath and spine flows in the jet. So perhaps the field could be reoriented at the edges to lead to local quasi-parallel configuration, where magnetic field is almost along the direction of the flow. For GRBs, the situation is actually quite favorable. So there we need low magnetization external shocks to produce afterglows. And those low magnetization shocks do seem to work in simulations quite well. They generate enough magnetic field to cause the dissipation. And the big question there is whether the field actually can survive for long distances behind the shock. And also the fact that we're seeing a lot of energy transfer between ions and electrons is encouraging. So the high electron energy fraction that people invoke in gamma ray bursts could be actually understood from the first principles in this simulation. So that's a promising direction as well. Okay, so that's the story about the relativistic shocks. Now let's talk about the non-relativistic shocks. Well, so here the story is a little bit more complicated. We were actually forced to go here. The mass ratio turned out to be an important quantity. We actually were forced to go all the way up to mass ratio of 1600 in order to see interesting physics. And what we find is that again, in the zeroth order, the shock structure depends on the background magnetization. And it depends on another way to say it depends on the authentic Mach number. And the authentic Mach number is thought to be quite large in these shocks. So if you just take the fiducial ISM magnetic field and take the velocity of the flow of a few thousand kilometers per second, you would arrive at authentic Mach numbers of hundreds. What we're finding is that we can accelerate ions quite efficiently if the magnetic field is quasi-parallel to the direction of the flow. So the magnetic field, the particles can escape along the magnetic field in front of the shock and then cross the shock several times and get accelerated. However, electron acceleration is a big worry because we see ion acceleration, but we didn't see much electron acceleration. The reason for that is electrons start with a big handicap. They're starting with a much smaller Larmor radii than the ions. So the shock structure happens on the scale of the ion Larmor radius. Okay, so the shock structure is the ion gyration. Now, as the electrons have tiny Larmor radii, they can never just cross the shock. They need to re-energize somehow. And this is what's known as the injection problem in the non-relativistic shocks. And this injection problem, I think we finally found a mechanism to explain this injection problem at least in the supernova remnant environment. So here's the story. Here's a simulation of a non-relativistic shock. So this is mass ratio of 400, velocity of 18,000 kilometers per second. We have to go a little bit higher than normal, but still it's a subrelativistic velocity. Mach number is 5 here, and the magnetic field is at 75 degrees in the direction of the flow. Okay, so this is the shock structure. What you see here is the density. Magnetic field does pretty much the same thing. It gets compressed together with the density. And this is the structure of the density in 2 dimensions. This is the structure of magnetic energy in 2 dimensions. And this is the phase space. So this is the incoming particles, incoming ions have negative momentum. When they reflect, they get positive momentum. So there is some reflection loop going on right at the front of the shock. And this is the momentum space of electrons. The interesting thing about this is, notice that in front of the shock, there are some interesting oblique structures that are propagating in front of the shock. These are waves that are generated by a shock. These are called Whistler waves. If you look at their polarization and the speed, it's the end of the branch of the alphanic modes. And it turns out that these Whistlers are doing something very interesting. These Whistlers can actually pre-accelerate electrons and cause the injection into shock acceleration. So here's how this happens. What I'm going to show you here is a trajectory of a representative electron that is coming near this. This is called the shock foot. This is the transition, the first transition of the shock, where the ions are reflected and that first gyrational loop of ions happens. And what you'll be seeing is the magnetic field is oriented this way. Here you'll be seeing the electric field along the x direction, and that's the x direction electric field, and this is the density, and here's the trajectory of this particle, and it turns out that these Whistler waves have an electric field component that's pointing along the magnetic field. So what you can see here is that this electron is starting to move faster and faster and faster than sliding along the magnetic field. So it's stealing this electric field generated by the Whistler wave and gets accelerated.
What? Wait a minute, sorry, I'm confused. You have Whistler electron-supported mode. The electric field is J cross E, isn't it?
Not really.
You know, classical Whistler dispersion. Pretty sure. Let's talk afterwards. But
We should, yeah. I can't claim I understand them completely.
this is supported by the whole term of conductivity, which is J. The electric field is minus J cross E.
Maybe they're not technically Whistler waves. And you see, they don't come with a label, but they, I mean, it looked like they were, so we should discuss it. Anyways, these mysterious waves have a component of electric field along the magnetic field. And so what's shown here is the energy gain of the particle in yellow. And green is the amount of energy gained from the parallel electric field. Okay, so almost all of the initial energy gain is from this parallel electric field. Okay, so at this point, particle already has some energy. And then it starts to basically sample the upstream and the downstream of the shock. So now most of its energy in red is the transverse energy gain that it gains from the transverse electric field. So this is now the kind of the shock drift acceleration or quasi-Burn acceleration. So you needed to pre-accelerate these particles, and then they start to sample the upstream and the downstream, and they gain interesting energy. So here is the spectrum that you get. So this is the Maxwellian component in electrons. This is the power law that we obtain. And the highest energy electrons that you see have the Larmor radius that's equal to the Larmor radius of the proton. So with pre-accelerated electrons, now they're pretty much the same as the ions as far as the shock is concerned. And the ions wouldn't get accelerated, the electrons would also get accelerated.
So this is a Mach number 5 shock?
No.
Mach number 5 shock?
Well, this particular one could have been 10, I think.
Okay. But it's a very steep spectrum.
-3.
But then you figure photons 2.4.
So 2.4 is a relativistic result. Non-relativistic is different. Now, one thing about this spectrum is that, okay, great, we've got some electrons accelerated, but look at the ions. The ions are not accelerated at all. That's because this happens mainly in the quasi-perpendicular shock. So the electrons could zoom along the magnetic field and get accelerated. Protons couldn't go far into the upstream. So I can either have electron acceleration or I can have proton acceleration, which is interesting, right? Because we can now play astrophysical games. Okay, why was this not seen before? The reason is that these Whistler waves, or mysterious waves, exist only when the Mach number of the shock is smaller than the square root of the mass ratio. So If you have a fixed simulation, the mass ratio is 25, and you're running a Mach number 10 shock, you're not going to see those waves, and you're not going to see electron acceleration. That's exactly what's happened in the literature. There's a lot of simulations with artificially low mass ratios and artificially high Mach numbers, which didn't see this. If you actually crank up the mass ratio, that's why we went to 1600. Now, when we do that, the Mach number that we can probe can get larger, and so we can use much, Mach numbers of 30 maybe can easily accelerate away. And you can see it in this plot. This is different mass ratios. 25, 100, and 400, you can see that the tail is growing with the mass ratio. Okay.
What fraction of the energy is actually going into the...
Okay, so that's an interesting question, but ultimately it's a little bit misleading because this process really cuts off here, right? What I need is for this to get another power law over here to actually go to ultra-relativistic energies. And if you want to have the number of electrons to be, what was it, 10 to the minus 4 of the number of electrons at high energies to 10 to the minus 4, then this puts a limit on the slope of this connector between the thermal and the non-thermal. And that slope has to be around 3. If it's much steeper, then you don't get a lot of electrons into the non-thermal tail. But the nice thing, it connects here almost up to the thermal peak. Okay, so what does this mean? On the one hand, I just told you that the alphanic Mach numbers are very large in supernova. On the other hand, I tell you that in order to accelerate electrons, they have to be small. So what is it? I think the solution is that these shocks pre-amplify magnetic field. So the initial orientation of magnetic field is probably going like that, and that leads to proton escape into the upstream. That pre-amplifies magnetic field and makes local alphanic Mach numbers smaller. So the local alphanic Mach numbers can reach around 20 or so, and that leads to local injection of electrons into the acceleration process. And then once electrons are pre-accelerated, they can sample the large turbulence on larger scales driven by the ions. So that's how the whole process probably unfolds. And so in order to do that, you need these cosmic rays that are riding in front of the shock and creating turbulence. So here's this simulation. This is the magnetic field. So there's cosmic rays riding through this box, and you're seeing the magnetic field along the direction of flow and transverse to the direction of flow. You're driving these Bell waves, and these are circularly polarized waves, and eventually it goes nonlinear. You start creating holes in the density. So this is the kind of process that we envision happens in front of the shock if the protons can escape.
But you relying on proton acceleration, right? You said that didn't happen.
Right. So it doesn't happen at a locally quasi-perpendicular shock. But if on a larger scale, the field is quasi-parallel, then you can amplify the magnetic field. It will cause local injection of electrons. But on large scale, protons can still escape. So here's what the shock really looks like. This is a hybrid simulation on much larger scales. And what you see here is the density profile through the shock. It's not a homogeneous flow. Right? There are pockets of cosmic rays blowing up the density here. There's holes in the density. The magnetic field in these holes is quasi-transverse. And it's quite turbulent here. So, and the magnetic field in the plasma is more or less quasi-parallel. So the injection of protons and electrons happens in different places along the shock phase. So the whole thing is more complicated. But I think we can make it an interesting story.
And roughly, what's the ion gyro scale here?
It's comparable to this hole, I think.
Is this, presumably you tried it at many resolution, is this a totally stable result with all the little bits being stable and peaks? I mean, obviously if you decrease the resolution, you're not going to get that. You increase the resolution, does it change?
Well, the scale of these things is driven by the Lama radius and the physics of these bell waves. I think the scale of these structures pretty much stays the same.
More dynamic structures that they long membrane.
Yeah, I think it doesn't, but we haven't tried too many things. This is fairly, this is like 8,000 CPUs for a couple of days. Okay, so the idea overall is probably if the supernova remnant shocks accelerate electrons efficiently, there should be protons in the background. And those protons are probably pre-amplifying magnetic fields and causing quasi-transverse shocks locally in the book.
So your estimation for the bright rings there is just before you got the magnetic fields running through those.
Yes, so these bright rims is because the field was pre-amplified in the upstream. Okay.
I mean, are you saying that why is it pointed out? Is there a background field already in that direction?
All right, yes. For this particular one, there is a background magnetic field. This is the remnant is a little bit off plane of the galaxy, so there is an interest in the galactic magnetic field that's thought to be pointing in this direction. There are certainly supernova remnants we don't display this on its orbit. Okay, so let me switch gears a little bit. Let's quickly talk about relativistic magnetospheres. So the thing we were trying to do here is to explain the new observations by Fermi about gamma ray pulsars. So there's an explosion of data now. We have more than 70 gamma ray pulsars throughout the galaxy, and they all come with this interesting morphology of light curves. So what you see here is the typical light curves are double peaked. The radio peaks come here, and the gamma ray peaks seem to be offset from the radio peaks. And they're typically these double humps, and the separation between the humps can change, but on average it's roughly half a rotation period. And what we try to do is to just construct a kind of a phenomenological model of this, just to see where the emission in the magnetosphere is coming from. And to do that, we used a more realistic shape for the magnetosphere that comes out of the simulations of the Pulsar magnetosphere with force-free MHD. So this is the shape of the magnetosphere that was derived with time-dependent simulations with force-free limits. So what you're seeing here is the evolution of the magnetosphere from initially all closed field lines. It forms open field lines which are asymptotically straight. The color here is the toroidal magnetic field. You can see that the field switches sign from one hemisphere to the other. And that means that there is strong current flowing in these current sheets in the equator. So there is a strong equatorial current sheet over here. In 3D, this structure is pretty much the same but tilted. And you have the closed field lines and open field lines. Again, there are strong current sheets flowing on the boundary between those closed and open field lines, and also between the field lines that are oriented in different directions in toroidal sense. Okay, so you can see how these current sheets is flapping up and down. Okay, so what we've tried to do is to take this geometry, which is different from what's typically used. Typically you use the Vickers field, which doesn't have this current sheet. So we've taken this geometry and just asked a simple question. Let's say we trace some flux tube in the magnetosphere. We assign emission per unit length of the field line to that field line, and then just count the photons, see where the photons fall on the sky. So what we've done is we've identified the polar cap on the surface of the star, and then we just drew concentric circles on the polar cap, and then traced the field lines into the magnetosphere. And the typical shape of such a field line bundle looks like this. And then you assign emission, and we'll see where those photons fall in the sky, including all the aberration effects and so forth. And this is the kind of a sky map that we produce. So what's shown here is that this is the shape of these field lines, and when you bend the photons, you typically bend this on this plot of the phase of the rotation versus the angle from which you're looking, the observer angle. And each field line has a certain color, and you can see how that color maps into this plane of the sky. So if you're an observer looking at a particular angle, as the pulsar is rotating, you will see photons from these field lines, and you won't see anything, then you will see photons from these field lines. Okay? And a typical, if you include emission from both poles, the typical curve on the sky will look something like this. If you were to cut it at some observer angle, you will in general see 4 peaks. 1, 2, 3, 4. So then you just vary which set of field lines you invoke, and you can see that for some field lines you actually form double peaks, like right here. So there is a certain set of field lines which manages to produce double peaks. Great. So we kind of know which field lines to trigger, but now why do we want to trigger these field lines? What's physical about it? Well, if you actually take those field lines and map them in the 3 dimensions, what you find is that the white lines here, the field lines that we prefer to produce this double peak emission. The red thing is the strength of the current sheet in the magnetosphere. So what you're seeing is that these field lines that we like seem to be hugging the current sheet quite well. So the idea is that you would see the radio emission come when the pole is looking towards you. So right now that you will see radio emission, then you will see one gamma ray pulse, and then you will see another gamma ray pulse right now. Okay, as this current sheet is sweeping our line of sight. So now we have a location in the magnetosphere where the photons are seeming to come from, and it's kind of different from what was assumed before using the vacuum field lines. Essentially, most of our power comes from 0.9 of the light cylinder and beyond. So we're actually invoking most of the gamma rays seem to be coming not from within the magnetosphere, but from the current sheet a little bit outside the magnetosphere. So around 1 to 1.5 light cylinder radius. And this is the kind of light curves that you generate depending on the inclination angle and the viewing angle. So why is this, what's going on? Well, this now points you towards plasma physics, because now we've identified, just on the basis of geometry, we've identified which region is likely to emit. We haven't specified anything about why it emits. Right, so now we can ask why. Well, the reason why is probably, that's the current sheet, so you're likely to have some sort of relativistic reconnection there. This is going to lead to a process that looks something like this. What you're seeing here is field lines in the force-free simulation with a little bit of resistivity, and this is the light cylinder. What you're seeing is when the resistivity is on, you're coalescing these field lines until you emit some sort of a plasmoid. So there's a rapid relativistic reconnection happening here, and it doesn't destroy the magnetosphere, but it controls the dissipation and the extent of the magnetosphere. So some sort of plasma heating that happens in this reconnection layer is going to be an important piece of the puzzle. And so far, the geometry is pointing in this direction, but so far, really, the physics is quite misunderstood. So we don't understand how relativistic reconnection works. But this is now an interesting plasma physics problem, which I think, once solved, will directly map into spectra of the gamma ray pulsars, since the light curves are already easy to reproduce using this location. Okay. In view of time, let me skip the MRI part. So I was.
What's the soundbite about the MRI?
Yeah, I guess the soundbite is this. So
you already heard about the basic instability.
Yeah, the basic instability MRI. What's happening is, and you start with the initial magnetic field, you try to pull it like this, and the MRI goes if the omega, the alternating frequency is smaller than the rotation frequency. Okay, so what I tried to do is to reproduce this instability with kinetic methods. So far it's been only shown in MHD in simulation. So what I've set up is basically a shearing sheet within the pictose, and this is the density profile. The magnetic field is initially zero net flux, so this is vertical direction, this is the radial direction. So the magnetic field is pointing up like this and down like that. And well, you perturb it, and what you find is that there is an exponential growth, and the exponential growth is consistent with what MHD tells you. So at least in the pair plasma, we can see the MRI happening in a kinetic collisionless limit. And that, it seems to have the right growth rates. Exact factors of 1.5 we're still trying to nail, but the general physics is there. And the ultimate dissipation again points to reconnection. So you're seeing the magnetic field doing that, and it's being torn apart, and you will see these islands of the flux tube basically trying to reconnect. And this reconnection now is modeled in a more or less self-consistent way. This code is kind of made for that. It's resolving all the plasma scales needed in this reconnection.
And where does one get pair-dominated disks?
Sorry, what?
Where does one get pair-dominated disks?
Yes. So the next thing is ions. So I don't have this result yet, but we're going to add ions, and that is going to get interesting. Now I see a lot of heating in this. So far I don't see significant non-thermal components, but there is a lot of heating that happens. As you make heating, the transient effect may look quite non-thermal. So the green line is the thermal distribution. As the sensibility proceeds, the distribution itself will look kind of non-thermal. Right? Ultimately, basically what's happening here is trying to keep the plasma. Ultimately, this turbulence dies. So the question is what happens in 3D, where the turbulence doesn't die, and you're always driving it. And that perhaps you may have this non-thermal tail all the time. I'm just guessing. I don't know. Probably not. But so most of the heating that actually does happen in the reconnection islands. So there is potential for some non-thermal effects that predicted.
It's sort of like the mirroring effect of ions is contracting and particle behaving.
It should be, but I haven't actually traced the particles. Okay, so let me conclude. I take too much of your time. So the conclusions is that basically I've shown you 3 examples where I think small scale and large scale can be connected. And I've shown you how we can model particle acceleration now in both relativistic and non-relativistic shocks. And we can see how reconnection pops up in several different places, including also magnetospheres, and now also in the MRI. And I think it's promising to actually try to understand reconnection. I started in this business thinking that I will never work on reconnection, but I'm more and more being guided towards that black hole of studying that process. Okay, so I think the basic open questions here is what is the microphysics of these individual processes such as reconnection or acceleration or heating, but also what keeps me engaged is how to connect all of this microphysics to larger scale. Because it's all fine and well to understand this in complete isolation, but really you have to be thinking how it affects the global system. And sometimes I feel that you can try to make these connections.
Save your questions. We can still talk to Anatoly upstairs, and let's thank him again.